how solutions are made, especially in respect to the intermolecular forces. So first off, we want to talk about what constitutes a solution. So a solution is when we mix two or more substances together. And in doing so, we create a new mixture, a new solution that is independent of the solute and the solvent. So the solute is what we have in the lesser amount, and the solvent is what's in the greater amount. So we can't think about it in terms of solids and liquids and gases, and we'll get to that later. We have to think of it in terms of amount. What do I have more of? What do I have less of? So when we start mixing a solute and a solvent, we have to think about how they're going to interact together. So as anyone who has tried to put oil and water together, you know they don't like mixing. They will separate back out into two distinct layers. So why is that? So if we look at the example of oil and water, we think back to our intermolecular forces. So water interacts through hydrogen bonding, which we've already talked about, and hydrogen bonding is a fairly strong intermolecular force. Oil consists of long hydrocarbon chains. So just carbon and hydrogens linked together in long chains. They are nonpolar. They're going to have only London dispersion forces. They have a great deal of surface area, so they have a lot of these London dispersion forces. They are not going to separate those London dispersion forces to try to interact with water. They can't hydrogen bond with water, so there's no incentive. Water is not going to break up these strong hydrogen bonds to try to interact with something that's nonpolar. So they stay separated into two distinct layers. Sometimes this is referred to as the like dissolves like argument. This can be talked about in terms of polar versus nonpolar, but really the like is about what type of intermolecular forces do you have. If you have similar intermolecular forces, even between two different types of substances like water and ethanol, because they can both hydrogen bond, they're going to be able to hydrogen bond together. If you have dissimilar intermolecular forces like hydrogen bonding and London dispersion forces, they're not going to interact together very well. So in the like dissolves like argument, we have to think about the interactions between the solute molecules, between the solvent molecules, and what new interactions would be between the solute and the solvent if they were to interact. So in the diagram on the right, we have our solvent-solvent interactions. So if we're talking about water, this would be the hydrogen bonding between water molecules. We have our solute-solute interactions. So if this were our vegetable oil, this would be our London dispersion forces. And then we have what potential interactions are going to be between the water and the oil molecules. And we have to think, are they similar to the types of interactions we'd have to give up to make the solution? Or are they very different? So we have some ideas we have to think about. The solute is not going to dissolve into our solvent if those new forces that we're making are much, much weaker than what we already have. Okay, hydrogen bonding is much stronger than London dispersion forces. There's a lot of London dispersion forces between oil molecules because they are so large. So those are strong forces that we cannot break up easily in order to make what would be a much weaker force between water and oil. So let's talk about the forces that we would have between solute and solvent. The first one comes from the list we've already talked about, ion dipole forces. This occurs between ions and a polar solvent, like water. So in our example with sodium chloride, we would have water molecules surrounding both the positive and the negative ions from the ionic compound when it broke apart. These ion dipole forces are fairly strong intermolecular forces, stronger than the hydrogen bonding of water by itself, so we can have those new interactions. So here's an example of how ions dissolve in water. We first have our polar molecule, and it has hydrogen bonding if we're talking about water or ethanol. we have to break up those hydrogen bonds and then form a new interaction with the charged molecule or charged ions. Once the ions break apart, then these new ion dipole forces would be stronger than the hydrogen bonding. Hydrogen bonding between solute and solvent follows the same rules it did before. We just have to make sure we have the oxygen, nitrogen, or fluorine in both the solute and the solvent. So water makes a very good polar solvent because it can do hydrogen bonding. It's polar, so it does dipole-dipole forces. So we can dissolve any kind of polar solvent in water. When we look at how other molecules besides water interact, we see a lot of hydrogen bonding as well. In fact, in biological settings, hydrogen bonding is crucial. It's how DNA interacts between the strands. It's how drugs interact with target molecules. It's how proteins interact with their binding molecules, how enzymes interact with their substrates. So we have a lot of oxygen and nitrogen and hydrogen in a lot of the proteins and molecules in our body, and they form hydrogen bonds everywhere. Dipole-dipole forces. Any two polar compounds can have dipole-dipole forces. They don't have to be similar at all. They just have to have an overall dipole moment. So we have a lot of different dipole-dipole interactions that are possible, as long as both compounds are polar. And then our last one, London dispersion forces. This comes down to nonpolar compounds interacting with other nonpolar compounds. So our vegetable oils, gasoline, all of these types of solvents are going to be able to dissolve nonpolar compounds fairly easily. Nail polish remover, acetone, even though it's slightly polar, has a very large nonpolar area, so it can dissolve both polar and nonpolar compounds because of this. So when we look at whether we can make a soluble solution with our solute and solvent, we have to look at those intermolecular forces. What forces did we have in our solvent? What forces were present in just the solute? What are our new forces going to be? If they are similar, the like dissolves like argument, then they can replace one another. Hydrogen bonding between molecules can be displaced by hydrogen bonding between water and ethanol. So we can mix ethanol and water together all day long. Same idea when we mix nonpolar compounds. We can mix octane, which is just a long hydrocarbon, nonpolar, with butane, which is just a shorter hydrocarbon, because they both have nonpolar tendencies, they both have London dispersion forces. When we try to mix something that doesn't have similar forces, we end up with the separate layers. They are not going to interact. Now, this gets a little bit more complicated when we look at overall compounds to determine what is the prevailing intermolecular force. And this really becomes evident when we look at alcohol compounds. So alcohols have the OH group, which we immediately should recognize as hydrogen bonding capability. And this would be the dominant type of intermolecular force in small alcohols. So in the first one here, methanol, we have an OH group and a very small hydrocarbon part with one carbon. And then we see as the hydrocarbon part gets longer and longer, that hydrogen bonding capability becomes less and less dominant for how it's going to interact with neighbors. And we see that with the solubility over here. So our short, small alcohols are totally soluble in water because the hydrogen bonding is most important. But as this hydrocarbon chain gets longer, solubility decreases. Even though it still has the same ability to hydrogen bond, that no longer becomes the dominant force. This hydrocarbon chain becomes more important. It creates more interactions with neighbors. It has greater surface area that is nonpolar. And eventually, even though it's an alcohol, long hydrocarbon chain alcohols become nonpolar and predominantly and insoluble in water. So when we look at how we can make a solution, a little bit of terminology has to do with what our solute and our solvent is. When two liquids completely dissolve in one another, like water and ethanol, I can mix any proportion of those any way I want and make a soluble solution. They are called miscible. Alright, so if I can mix any two liquids and make a homogeneous solution, it is miscible. If two liquids cannot be mixed together, or cannot be mixed together in any proportion, like there's a limit, I can only mix a little bit before it starts separating, those are called immiscible. Alright, so when we look at acetone and water, water being polar, acetone slightly polar, we can have hydrogen bonding between water and acetone, I get a homogeneous solution. When I start mixing water and methylene, which is a hydrocarbon, only carbon and hydrogens, it just has a double bond in there, London dispersion forces only, I do not get a homogeneous solution. I get a separation of the polar and the nonpolar. So let's look at some examples. We've talked about ethanol and water. Ethanol, being a short alcohol, can form hydrogen bonds with water molecules, so I can get a homogeneous solution. Pentane, which is just a 5-carbon hydrocarbon chain, and octane, which is an 8-carbon hydrocarbon chain. Both have London dispersion forces, they're both nonpolar, so we're just looking at having London dispersion forces between them, so this would also make a perfectly soluble solution. Carbon tetrachloride, you remember that's CCl4, so 4 chlorines attached to a central carbon, versus ammonia, which is NH3. Carbon tetrachloride is nonpolar. All of the polar bonds get canceled out through symmetry. Ammonia is a polar molecule with NH bonds. So ammonia can form hydrogen bonds with its ammonia neighbors. Carbon tetrachloride only forms London dispersion forces with its similar neighbors. So if I try to mix these two together, this will not form a soluble solution. Their intermolecular forces are too dissimilar. Naphthalene, which is also a hydrocarbon, not a long chain, this actually has a double ring, but still completely nonpolar, trying to mix with a polar solvent water would also not create a homogeneous solution. Again, the hydrogen bonding in water is not going to break up in order to interact with London dispersion forces from the naphthalene. So even if we don't know too much about these substances, if we can look at their intermolecular forces, we can get an idea about their solution behavior. Alright, so to talk about a few other types of solutions. Gases I can mix together in any proportion I want. It doesn't matter their intermolecular force. And that's because gas molecules are too far apart. They're not actually interacting. Gas molecules get as far away from each other as possible. So I can mix any gases together that I want. And the greatest example of this that everybody has experienced is our own atmosphere. It is not composed of only oxygen and nitrogen, that makes up a majority, but there are a lot of gases in our atmosphere at any one point, and it creates a homogeneous gas solution. There are also solutions of solid solutes and solid solvents. This might be hard to imagine. How do we mix two solids together to make a homogeneous solution? Really, this comes down to melting solids, mixing them, and then allowing them to refreeze into a new solid. Alright, and we have two kinds of these. Waxes, which I'm sure everyone is familiar with, and alloys. Alloys is our term for a metallic mixture, a metallic solution. And we have two types of alloys, substitutional and interstitial. We're going to talk about both of these. Substitutional is when we have one atom replace another atom in the matrix, in the lattice that solids have. And interstitial is when we have a second type of atom fit in between atoms of the first. So let's look at what this is. So our substitutional. Substitutional alloys have one atom replace another in the lattice. So most people have heard of brass. Brass is not an element on the periodic table. It's not a metallic element. It's actually a solution. It's a mixture of copper and zinc. Okay, the different proportions of copper and zinc that you have make different colors of brass, different strengths of brass. But the zinc molecules are replacing the copper molecules in the lattice. So it's an alloy. Gold, 24 karat gold, is what we consider pure gold. But if anyone has 24 karat gold, they know pure gold is pretty soft, easily scratched, dented, bent. So people started replacing the gold with copper and silver, and that lowers the carat. Okay, so the more copper and silver that you replace into the gold lowers the carats, but strengthens the metal. So 14 karat gold will not scratch and dent as easily as 24 karat, and it's usually a little cheaper. But it's still a solid solution. Interstitial alloys have a second type of atom in between the atoms of the first. Steel is the best example of this. Most people have heard of steel. It's much stronger than iron by itself, and that's because we have carbon atoms fit in between the iron atoms to make the steel. So this closer packing, more interaction creates the added strength that we see in steel over iron. Alright, so that's the end of what we're going to talk about with how solutions are made. In the next video, we're going to talk about some characteristics and a little bit of the